For scientific and medical discovery, it is very important to capture the individual dependencies of shapes on covariates. For example, growth charts are used to describe how children's height and weight change with age. Brain charts are used to describe how the brain characteristics change with age. Beyond the charts for 1D characteristics, a 3D shape representation is needed to describe how different covariates affects 3D shapes. For example, we'd like to know how the brain shape changed across time, or how the airways develop after from birth to adultness. Neither is such a shape representation which can extrapolate from incomplete, entangled, and individual observations to the complete, disentangled, and universal shape space. Specifically, NICER aims to answering the following questions. Given an atlas shape, how can one accurately represent individual shapes? Given a shape, how can one disentangle different covariate effects from each other? Given a covariate, for example, age, how does the shape evolve based on this covariate? Given a random shape, how will the shape develop after a period of time? NICER is the first implicit shape representation method to investigate an atlas-based representation of 3D shapes in a deformable, disentangleable, evolvable, and transferable way. NICER is a template-based neurodeformable representation. Each shape can be represented by an overall displacement imposed to the template shape. The overall displacement can be aggregated by covariate-wise displacements. During training, we learned the templates and MLPs for covariate-wise displacements. Zero latent codes would give no displacement to the template shape. At test time, we evaluate the trained MLPs for shape reconstruction, evolution, disentanglement, and shape transfer. The training losses are composed of a regularizer for latent codes and shape reconstruction losses. We evaluate NICER on 3 datasets: Starman, a simulated 2D dataset, the ethnic hippocampus dataset, and the pediatric airway dataset. In the Starman dataset, there are longitudinal observations for 1,000 Starman in the training and testing sets, respectively. Each Starman is associated with 2 covariates, controlling the movements of the arms and the legs. The ethnic hippocampus dataset consists of 16 32 hippocampi. Each shape is associated with 4 covariates: age, sex, whether this person has Alzheimer's disease, and educational length. The pediatric airway dataset consists of 357 upper airway shapes. Each shape is associated with 3 covariates: age, weight, and sex. Compared with other shape representation methods, NICER can produce realistic, complete, and accurate reconstructions on the Starman, hippocampus, and airway dataset. Only ASDF and NICER can deal with covariates. ASDF performs better for Starman, but NICER works better for realistic datasets. This is because the neuroadditive network design can naturally prevent overfitting. Here is an example of the shape transfer task. This is the airway of a child who is scanned for 11 times. Given a new airway shape, we estimate the latent code from T0 and transfer the shapes to T1 to T10. For shape evolution and disentanglement, ASDF and NICER both produce high-quality Starman shapes because the longitudinal data is sufficient. However, for real data, only NICER can produce realistic 3D hippocampi and airways reflecting the covariate influences on template shapes. NICER can also produce high-quality shape extrapolation for a specific patient by designating the latent code Z. Please check out our paper for further details such as implementations and applications. We released our demo and source code. Feel free to try them out and give us a star if you find this work useful. Thanks.